In this section we'll be looking at bisectors and triangles. Mostly we'll be looking at perpendicular bisectors and angle bisectors. Now these are lines that can be drawn from the triangle, and one of the things that we're going to notice is a lot of times these lines are going to meet in the same point. And when you have three or more lines meeting at the same point, we say that they are concurrent. They're all meeting in the same point. And we can call that point a point of concurrency. So there's going to be some special things we'll learn about these points of concurrency. Now the first one is dealing with perpendicular bisectors. So remember, we have a segment at the midpoint and a line perpendicular to that. Now something that we'll notice then about these perpendicular bisectors is, first of all, this is our perpendicular bisector, and we can see that as we move our triangle around, it'll end up in different places. And if we look at all three of them together as we move this around, notice that those three perpendicular bisectors are all meeting together. Now sometimes they're going to meet inside the triangle, and sometimes they're going to meet outside of the triangle. And this is a special point. This special point is called the circumcenter of the triangle. This is where the perpendicular bisectors meet. Now there's something else that's interesting about these perpendicular bisectors. If I were to draw a circle from that point of concurrency, that circumcenter, and I go to any one of the points on my triangle, it's going to be the same. Basically, this point is the same distance away from every corner of my triangle, so no matter which point I choose to use, that circle is going to go through all three of those points on the circle. And this is our first special, and this is called the circumcenter. We can also say that the circle is circumscribed about the triangle. Now if we want to prove this, this might look a little crazier, but here we've got a triangle and all of our perpendicular bisectors of this. Now what we're going to use to prove this is the perpendicular bisector theorem. Now remember, this was where any point on the perpendicular bisector has to be equidistant from the corners. Basically we're forming an isosceles triangle. So notice what I have here. I have three isosceles triangles that came from cutting up these different perpendicular bisectors and connecting that point P, the center there, to the corners of my triangle. So if I bring each one of these together, notice that with all three of those isosceles triangles lining up together inside of the triangle, since each one is an isosceles triangle, because it's on the perpendicular bisector, so in each one of these triangles, we know these are bisectors because that's what was given to us, and therefore we know that each one of these sides would be congruent. In this one they would be congruent to each other, in this one they would be congruent to each other, in this one they would be congruent to each other. And if we remember that PC is the same length, then those two are congruent to each other. Basically we should see that all of these lengths, CP, AP, and AB, are all the same. So we can see this better if we put all these back inside of our triangle here, and we'll notice that this point P is the same distance from each corner of our triangle. Now this is going to happen, sometimes it'll happen within the triangle, sometimes it could happen on the triangle, or sometimes they could meet outside of the triangle. One way that we can use these is if we want to find a way to place something in the middle of 3 points. So here I have 3 trees. The town planner wants to place a bench exactly in the middle. Well, to do that we can connect the sides as a triangle and construct the perpendicular bisectors. If we do that correctly, so each side is at a midpoint and each one is perpendicular, then they're all going to meet at the same point, and this is the circumcenter, and that will be where it is equidistant to each one of our sides. So the distance from that center to C, the distance from the center to B, and the distance from the center to A will all be the same. The next thing we'll look at are the concurrency of angle bisectors. Looking at angle bisectors, remember angle bisectors are segments that cut the angle in half. So if we're in the triangle, it's going to pass through and cut the other side. Now notice it's not necessarily cutting the other side in half. In fact, we can see this side is a little bit shorter than the other side, so don't assume that. But what it is doing is it's cutting this angle in half. Now if we look at 3 of those together, notice that those are always going to meet in the same place. So I'm just cutting each angle in half, and those bisectors are meeting in the same place. Now another property that's going to be true about that with any angle bisectors we saw in the last section is that it's going to be the same distance from either side. And so another property that ends up happening from this is if I were to take a perpendicular here, and it can be a perpendicular to any one of the sides, it doesn't really matter which one, but using that perpendicular to the side, if I connect a circle from the center, a point of concurrency to that side, notice this circle is going to touch each side exactly once. And so our Theorem 5.7 is about the concurrency of angle bisectors. It's telling us that these angle bisectors meet in the same place. It's also telling us that from that point, each one is the same distance from our sides. Okay, so we see PY here, XP here, and ZP. Each one of those are the same distance. And that's why we were able to draw a circle that touches each side exactly once. This then is called the incenter of the triangle, and we say that that circle is inscribed in the triangle. We can use the incenter then in a case like this. If we notice from our picture here, we have angle bisectors marked at each corner, so we know that CG, BG, and DG are all, AG are all angle bisectors, and these are perpendicular, so we therefore know that each one of these is the same length. So we're asked to find about GE and GF. Notice that those are the points drawn from our incenter, so we know that they have the same length. Again, it's important that it's marked as perpendicular and we have all the angle bisectors marked. That ends up with x equals 11, but we're asked to find GD. GD would be the same as either one of these, so if I find, say, GE equals 2 times 11 minus 7, that would give me 22 minus 7, or 15, then all of these are going to be 15, including what we were asked for, GD.